There we go. Wait,
Okay, welcome everybody to this. Yeah, I actually gave her some photo, but there's more order. Okay, welcome everybody to the SCC seminar, one standard time. We're very happy to have Mitali Bafna from UW visiting us. Mitali was a grad student at Harvard. She's an academic sibling of mine. She did her PhD with Madhu. Since then, she did her postdoc at CMU and MIT and has been faculty at UW since last year.
No, it's September.
Since sometime last year. Mitali, since her postdoc days, has been working on some amazing results in HDXs, especially direct product theorems, which eventually culminated in this grand result of short PCPs, 2 query PCPs with arbitrarily small constant error, which is what she'll be talking about. This is joint work with No, Dor, Nikhil, and Vik.
Okay, thanks Prahlad for the introduction. So today I'll be talking about this work on building efficient PCPs from these objects called HDXs. So I'll introduce everything and please feel free to stop me with questions. So let's look at what PCPs are. Many of you might have seen this definition. Imagine that a prover tries to prove some claim to you and gives you a really long proof for it. So one way you can verify this proof is to go through it line by line. And this will take time at least linear in the length of the proof because you have to read everything. So now the question is, can we do it faster? And PCPs give you exactly a way to do it faster. So instead of giving just the proof, the prover gives you an encoding of the proof in a more redundant format. So that you as a verifier can toss a bunch of coins and randomly query only constant number of locations in this proof and verify whether these locations satisfy some constraint or not. And based on this verification, you can output accept or reject. And the guarantee of the PCP is that if the prover did everything correctly, or did the encoding correctly, and the proof was a valid proof for your claim, then you will always accept this new proof with probability 1. But because now you're only checking few locations, if the proof was wrong, or if the claim was wrong to begin with, then you will never accept whatever the prover gives. So anything the prover gives you for a false claim will be accepted all but with some small probability of error.
Wait, so this is the correct encoding of the wrong. That will be accepted with small probability.
Yeah, so that's a good point. So imagine that the claim is wrong in the so-called no case. Then a correct encoding of the proof will be accepted with small probability, but actually anything that the prover gives you. It may not be even an encoding of a proof. You want that anything it gives you will also be accepted with small probability.
But I can do the same thing with one symbol off. How would you accept it?
But basically the encoding of a proof is also accepted with small probability, and anything close to it is obviously accepted with small probability. But anything far from it is also accepted with small probability.
Your constraint may depend on the claim also.
Yeah, everything depends on the claims, like the constraints you're verifying.
So if the claim is wrong,
Yeah.
then there is nothing that the prover can give that will make you accept with overwhelming probability.
Correct.
Yeah. So
the guarantee is.
So the prover is giving the proof or the encoding?
the prover is giving the encoded proof or the purported encoded.
Yes.
The guarantee is, the first guarantee is only for claims that are true. The second guarantee is only for claims that are false.
Okay.
Yeah. Yeah, sorry, I should have said. So this is like the yes case where claim is true and no case is where claims. So like imagine for a claim, just imagine a 3-sat instance which is satisfiable in the yes case. and no case it's unsatisfied.
So we don't care about for a correct case, you give a
Wrong.
wrong proof. No, I don't care about that.
There it becomes a bit murky.
Yeah.
How beautiful. Okay. Okay, so any more questions about definition? Okay, so there are two parameters that we are interested in, which is the obvious two parameters. So one is the size of the proof, like we want to minimize the overhead in this encoding. And the second is the error probability. So obviously we want to drive both these down to as close as, so size we want to drive it down to, ideally linear in the proof length, and error we want to drive it down to close to 0. And this has led to like lot of works studying these trade-offs. And today we'll focus on 2 query PCPs. So in some sense, this is the most stringent setting, because in one query, the verifier cannot verify anything meaningful. So 2 queries, you can ask that what's the best size versus error trade-off. And this is important for the setting of applications of PCPs to hardness of approximation. So I'll discuss the corollaries in a bit. Okay, so let's look at the size versus error trade-off. And in all these results, we fix the alphabet size, like each location is only allowed to contain a constant number of bits, each location in the encoded. So the first result is, of course, the famous PCP theorem, where they showed a size which is polynomial in the length of the original proof, and the error was something close to 1. So you will accept wrong proofs with quite a large error, but still bounded away from 1. And then this breakthrough work of Raz, called parallel repetition, which many of you have heard of, showed how to reduce the error of 2 query PCPs. So he could get it down to any small constant error, like 0.99 to the k, while blowing up the size by roughly n to the k. And then there was a lot of work also by Prahlad and many other people on reducing the size of 2 query PCPs. So what is the best you can get? Can you get it down to a linear size? And this culminated in the work of Dinur, who showed how to get n polylog n size PCPs. So just a mere blow up of polylog n, while again matching the error of the PCP theorem.
The size of the alphabet.
Yeah, in all these results, like today we won't be looking, as in we just think of the alphabet as a constant number of bits. So in this, like in this actually, when you drive it down to some small constant error, the alphabet size will be like poly and 1 over the error, something like that. But it's still a fixed constant if your error is a constant. Okay, so any more questions? And so the one question that arises is, can you get the best of both worlds? Like, can you get small size PCPs and small error simultaneously? And there was an amazing work of Moshkowitz and Raz, which was like towards this question. And actually, they were able to even get sub-constant error. Like the main motivation there was to get sub-constant error. But in this constant error regime, they were able to get nearly linear size PCPs. So not n polylog n, but like something almost linear PCPs. And interestingly, there were also a bunch of very interesting barriers shown to actually, improving the error of Dinur's PCP or improving the size of Raz's PCP. So these you might have heard of Bogdanov's work and pi gigabyte. And using HDX, we are able to match, get the best of both worlds that overcomes these barriers. And any questions?
What kind of
So I will mention like Bogdanov's barrier and see how it helps, how high dimensional expander.
compared to Moshkowitz Raz, the size is n polylog n and not n to the 1 plus little of.
Yeah, but it's also like Moshkowitz Raz is better in the sub-constant error regime. we are better in the constant error region.
So sorry, does this PCP also yield something when the error is sub-constant?
It will yield something, but it will be like as soon as your error is 1 by log n, this PCP will be much worse than Moshkowitz.
Okay.
Like it will become poly in n. Yeah.
So in the sub-constant regime, the Moshkowitz is still better.
Yeah.
And what is the alphabet size has to depend on how small this small constant. What is the dependence on alphabet
It's the
size?
same dependence that Moshkowitz or like
So
your
Moshkowitz is
paper.
about the alpha. So there's difference. So parallel repetition based, if the error is delta, the alphabet size is log 1 over delta.
No, this will have like poly delta.
Whereas
But
Moshkowitz is already poly 1 over delta, and this is also
yeah. Because it uses these alphabet reduction techniques.
Okay.
It uses Moshkowitz-Razov and your paper. Yeah.
No, I want to know, is it just that, or is there something, is it poly 1 over delta, or is it x 1 over delta?
It's poly.
It's poly 1 over delta.
I hope I don't have a typo there. Like later I will mention the formal result. But any more questions?
And technically, these are not barriers to the PCP construction. These are barriers to methods that yielded the PCP construction.
Yeah. They are all barriers to methods. So it's not like, okay, there is no PCP.
Yeah.
So these are barriers like to expander-based PCP or like specific parallel repetition, de-randomizing parallel. Okay, so in the next part of the talk, I will describe our formal result, like all the parameters and what corollaries it gives for hardness of approximation. And then I will give you overview of the construction of the PCP. And finally, I will end with like one of the main components, which was constructing fault-tolerant networks. Okay. So to actually formally state the result, it's easier to take the view of PCPs coming from constraint satisfaction. And many of you again might have seen this equivalence before, but let's give a quick reminder. So we can view any, so we'll focus on two CSPs where your CSP, each constraint only looks at two variables at a time. So basically this 2 CSP on alphabet size k can be just specified using a graph where each vertex is a variable and each edge has some constraint on it. And this we'll call as a constraint graph. This turns out to be like the structure of the constraint graph turns out to be very important for our results. So we'll call this like a 2 CSP on this graph. And we are interested in two parameters. One is the value of the CSP, which is the maximum fraction of constraints that any assignment to the variables can satisfy. And the size of the CSP, which is just the number of variables plus the number of constraints. And throughout this talk, like when we say 2 CSP on a graph G, you can also just imagine graph coloring. So graph coloring on this, on the constraint, on the given graph. Okay, so this is like an example, just K coloring. Okay, and the interesting thing is a PCP with error epsilon and size f of n is just equivalent to reducing 3-sat with value, in the yes case value 1, no case unsatisfiable, so value less than 1. Size is like the number of variables to a 2 CSP with constant alphabet, where in the yes case your value is preserved and no case your value becomes epsilon. So from just slightly less than 1, it drops to epsilon. And the size, like the number of, like the blow up in the reduction is just f of n. So then in this view, we can kind of forget about proofs and so on. Okay, so any questions?
So what is the value? They are not integer valued values, no?
Oh, yeah. So value was the fraction of constraints. So here, actually, the value is like if you violate just one constraint, then the value is 1 minus 1 over n, and we are dropping it to some epsilon close to 0. Okay, so our result stated in this language is
Is
just,
there an equivalent, not equivalent, a similar characterization if I have a 3 query PCP or something?
yeah. So 3 query will just become 3 here.
it'll
So,
be
okay, so with query Q will just be QCSP.
hyperparameter.
Yeah. Yeah, but because we are focusing on 2 query PCPs, we'll always have 2 CSPs. Okay, so stated in this language, we can put in all the quantifiers now. So suppose you want a target epsilon for your soundness. So for all epsilon, there is some large constant C such that we can reduce 3 sat with value 1 goes to 2 CSP with value 1, and no case value 1 goes to value epsilon. Whereas the blow up in the size is n polylog n, where the exponent of the log depends on the error you're shooting for. And also this alphabet depends on. Alphabet dependence is like poly 1 over epsilon.
Is there also a smooth-ish trade-off if you were allowed to increase the number of queries? I mean, can you get smaller and smaller PCPs?
Yeah, that's a great question. We haven't studied that.
So something in this reduction is really tied to the being a 2.
Yeah, we were just studying like 2 query agreement tests and so.
Smaller in terms of the exponent?
Yeah, I mean, I don't know if you're allowed 7 queries, you get 10 log n, and if you're allowed 20 queries, you get n root log n. I don't know, something.
Yeah, that would be interesting to study. Like these, are there anything known in that direction?
There's nothing known, but I think you can't believe us if you can do it with 5, you can do it with 2. So
No, but with the length slightly
the
increased.
length doesn't improve. What might improve is the soundness. Epsilon every additional query might make the epsilon a little smaller. Yeah.
But then the length, like dependence might improve, right? Because you're
When you can afford to start off with
Yeah.
something for smaller epsilon.
It'd be very hard to rule such things out, right? Because if there are
It's very hard to rule something. The gut feeling is it doesn't.
So maybe a request of primer. So like how does Basta's result sit in this thing? So you have 7 over 8 is the value there.
Oh, actually, I will get to Hastads in the next slide.
Oh, but that'd be 3 query.
Yeah, so actually here it's like very generic, the reduction here. You're not getting any interesting 2 CSP. Like
Oh,
this is
so
some
here-
generic thing.
So the clauses that you verify.
Yeah, there's some arbitrary clauses and so on. In Hastads, like the important thing is to get it to 3 sat, like these clauses to be 3 sat or 3 lengths.
So this should be compared to Raz's output of parallel operation, not to Hasta's. So this is before the whole Fourier analysis starts off. Yeah.
Oh, so that part is actually like changing what you verify. Like,
What you verify,
Yeah.
the gadget becomes
Right.
important. Here, this is the constraints are arbitrary.
Yeah.
In fact.
Also here the alphabet is large, like there if you have 3 sat, it'll be just bits.
Yeah.
Say you can't rule these things out. In principle, one can prove roll right? It's like property testing kind of rule.
You can prove algorithm, I guess. Algorithm.
In the construction of the PCP,
Uh-huh.
the proof, you do not constrain it to run in polynomial time.
Yeah.
Oh, you do.
Yes, we do.
Yeah.
You do.
So-
I think the only way to rule it out is just prove a algorithm, right?
No, like if I want to prove a lower bound on the length of the proof with a certain number of queries, this is an algorithmic question or is an information theoretic question?
It's
I
an
think
algorithm.
It's an
algorithm.
algorithmic.
You have to show, yeah.
Okay, that is very.
Yeah.
Yeah.
Yeah, because the implement in the verifier means verify that whatever question it was, it's over time, how
Yeah.
long time, you can just check.
Yeah.
And then we can look at the.
Yeah.
Yeah.
Yeah, so I'll show you the corollaries which will make it clear that it's a lower bound for PCPs is algorithm. Okay, so assuming exponential time hypothesis, which you might have heard of, it is just saying that deciding 3 sat or just distinguishing yes from no, sat from unsat requires exponential time. Under this, you can show that even approximating 3 sat takes exponential time, nearly exponential. So if you want to approximate it to a factor which is better than random guessing, so 7 over 8 plus epsilon, that will take time 2 to the n by polylog n. So literally the size of our PCP just goes into the, the running time of your algorithm.
So without the near linearity, this would have been 2 to the n to the epsilon or
Yeah.
n to the delta type thing.
Yeah.
But now you can get basically 2 to the n over polygon.
Yeah, actually with Moshkovitz RAS, you would just get,
Ah.
it is better than that actually. So you get 2 to the n by 2 to the square root log n something. Yeah. So yeah, that's what I was saying. So if you have want to prove a lower bound on the size, you can just prove a better running time for 3 sets.
No, I see. It's obviously you have the input and then you're looking at the proofs. Stupid way. But I mean, in this decoding, typically, sorry, you said
Yeah.
it might be just a distraction. But in this decoding algorithms, are they like really low complexity? Like, is there an AC0 circuit that can,
Oh,
even
the verifier.
verify?
The verifier is very simple.
Right?
Yeah.
So one can hope to still prove a lower bound that if you want an AC0 circuit, I'm just trying to answer his question. Yeah, like if you can try,
No, but even 3-sat, like, don't you, like the verifier here is very, yeah. I was just saying the verifier in 3-sat is also very simple, right? But we still have to.
No, so I'm trying to understand whether with a very simple verifier, now how do you make this verifier, how do you formally say a verifier simple? You assume that the verifier comes from a circuit class.
Yeah.
And now I say the circuit is very simple with whatever simplicity for which we can prove lower bounds, then the length of the proof has to be so much.
But I think that's the same as like saying that you will require large
I don't see
time.
why in principle why we can't prove. Okay? Because usually a verifier is assumed to be a polynomial time verifier.
No.
Oh, the verifier is
Just
very
three
simple.
sets, it just takes 3 bits and
Yeah.
checks the all of them as.
Yeah.
Oh.
Like the verifier here.
You don't have it against this guy, so
Yeah.
it would be very, very hard. It's
Like-
a lower bound.
Yeah, the verifier here, like
Or
what's
even
that?
3 elements sitting there, yeah.
Yeah, so the PCP is literally equivalent to this statement. Like the PCP,
Yeah.
this is just a random clause. So. And we also show some results in parameterized world. So this extends to PCPs in the parameterized world, like finding fake leaks in better than n to the k time. Okay, so now let me get to more interesting stuff, which is how to use high dimensional expanders. So recall that this is our goal, to start with 3-sat with n variables and reduce it to 2 CSPs with n polylog n variables, but in the no case, you have very small n. And we'll not talk much about the yes case, like all our reduction will always preserve value. Okay, so firstly, we can always use Dinur's reduction to query PCP, which gives you value 0.99 and only blows up by polylog n. And then the goal is to do this amplification from 0.99 to 0.0. Okay, so it's very instructive to look at Dinur's PCP because the ideas are very similar. Okay, so
Actually, can you just go back? So, already Dinur you can get 0.99. To get even 0.5, we did not know how to do it.
Yeah. I'll describe the 0.5 barrier actually.
Okay.
Yeah. Okay, so let's just recall expander. So how most of you have seen expander class. G.
Just define it anyway.
Yeah. So, okay, we should just imagine them. We won't be like going too much into details. We should just imagine them as like very well connected but constant degree graphs, where they have many of the properties that are possessed by complete graphs. So one such property is that if you take any small set of vertices, then it has a lot of edges, or like a lot of edges going out of the set. Okay. So let's see why they are useful for PCPs. Like at the first glance, it seems it's totally unrelated to proofs. Okay, so our goal in a PCP is to take like some proof with one error and convert it or encode it into a proof which is more redundant and has many errors spread across the proof. Okay, so let's be more formal. So imagine we have this 2 CSP, which is just 2 coloring on an expander graph. So given an expander graph, And the 2 CSP is just in the yes case, it's 2 colorable. In the no case, it's not 2 colorable. And we want to build a PCP for this. So one way to give a proof is just to give a green or blue assignment to the vertices. But Dinur's idea was, but this might have just one edge. So a verifier which just queries the edges will only notice an error with probability 1 over n. So Dinur's idea was to instead ask the prover to give an assignment not just to one vertex, but to a neighborhood around the vertex. So just the way to encode this assignment is that at every vertex, like at vertex 1 here, this location contains the assignment to its 10 neighbors or neighbors. So you just fix like at every location you give the value of the vertex and the coloring to its neighbors and the coloring to its neighbors. And now given this assignment, there's a simple 2-query test we can perform. So that test is just that verifier will pick 2 neighborhoods which have an overlap. It will test that, on the overlap, you should have given the same assignment to the overlap. And of course, you can also check that both neighborhoods should be colored correctly, should be 2-colored. So, yeah, so this is the obvious test. Any questions about this?
So why 2 coloring? I mean, like, isn't it?
Yeah, 2 coloring is not so useful for NP. We won't want 3 coloring. So actually this, you can of course extend it to any 2 CSP, but 2 coloring is useful to mention the barrier in the next slide.
Oh, right.
Yeah.
Okay.
What is the radius of this neighborhood?
So she takes it, like if you want some particular amplification, yeah, some constant, depending. You just have to pick some large constant like that. Okay, and this key insight is that you can use the expander graph to show that, if here you had epsilon fraction of your edges were colored incorrectly, then this test rejects with or accepts with probability only 1 minus 10 epsilon. So here your test was accepting with probability 1 minus epsilon. Here it will accept with smaller probability, so 1 minus 10 epsilon. And then iterating this procedure, you can get a 2 CSP which has value 0.99. Like in one step, you increase the gap by 10, then you do some steps of alphabet reduction. Again, you increase it by 10 and you keep going. And finally, your value becomes 0.99. Okay, so the obvious question is that why 0.99? Like, why can't we just keep doing this again and again and get down to half or even below half? Okay, so that's where Bogdanov noticed that there's actually a barrier to this approach of using expander graphs. And the main issue is that generic expanders, like there are expander graphs where locally they look like trees. So every local neighborhood is just a tree, and trees are always 2-colored. So what a prover can do is to totally ignore this assignment and actually just give a random, like a cheating assignment, a totally different assignment. So it's not given assignment which is not an encoding. So imagine that this graph is not 2-colorable. So there is no 2-colored assignment. But here what a prover does is at every location, it just tosses a coin, gives a blue or green assignment to the location, like to the vertex corresponding to that location, and then just propagates the assignment correctly to its neighbors and neighbors. So at every location, like the assignment will be perfectly 2-colored. And now a verifier can discover an issue only when it tests consistency between, because actually this is not at all consistent with any assignment to the vertices. It's just like some random garbage that the prover has given you. Okay, so any idea like what will be the probability that the verifier notices an issue? when it tests consistency between two neighborhoods. Yeah, so it will be at most half and exactly half. Just because like the union of the neighborhoods is also a tree. So as long as these two were consistently picked with probability half, there'll be no issue. So this is the issue with expanders, that they are locally two colorable, but of course there are globally there are expanders which are not even far from two color, but locally they will always look two color. Okay, so any questions about this? Okay, so that's where many people in the community like Dinur, Kaufman thought that we should go to high dimensional expanders. So they thought, so what are high dimensional expander? So these are like expanding hypergraphs. So instead of one edge, you have a universe of vertices, which is just these blue dots. And instead of having just edges, you have hyper edges on these vertices, collection of hyper edges. And again, you only have theta and hyper edges. But these hyper edges sparsify the complete hypergraph, where you have all possible hyper edges. So by sparsify, I mean that they have many of the properties that a complete hypergraph has. So one such.
When you say all possible, you mean all possible hyper edges with a different size or just one?
Oh, sorry. Yeah, we fix the size of the hyper edge to be like some constant. Like here it's 6. So all possible just means it has n choose 6 hyper edges. Okay, so one advantage, or like what's the definition, kind of just a intuitive definition of high dimension expanders, is that like one such definition is to just replace every hyper edge with a clique. So you get a graph, right? After you do this replacement. And now you want that this graph has the property that if you look at any vertex and its neighborhood, the neighborhood of every vertex is itself an expander. So clearly this is not true in the case of expanders, like a look.
A hyper edge of, let's say, 6 vertices.
Yeah.
Then build a normal graph over the 6.
Yeah, so you take a hypergraph.
You superimpose a clique.
Yeah, that's right. So
Yeah.
6 you have a clique of those of K6 of some.
Yeah, so which means
Yeah.
the new graph will now have order n times 6 choose 2 edges in it.
And then you are looking at the graph that you get out.
Yeah. One way to define it, like there are a lot of definitions, but one way to think of it is to just do this replacement, and then every vertex neighborhood you want it to be an expander, and like every edge neighborhood should be an expander, and so on up to like 5 cliques. If you take 5 clique and look at the neighborhood, that should be an expander. But notice that this is the property exactly which had the issue on the previous slide. Like we had this locally tree-like neighborhood, which is not an expander. Actually, if we remove the middle vertex, it's even disconnected, the neighborhood. And actually, this will help us solve this precise issue. Like if you consider two coloring on an HDX, it's not two colorable. And now the PCP, which asks the prover to just provide assignment on triangles, this PCP will have error 0 because triangles are not two colorable. So it avoids the issue on the previous slide.
So once again, when we are talking about coloring, we are assigning a color to a vertex, not a hyperage.
Yeah, we'll always only
Okay.
look at two CSPs on graphs. So yeah, but
So-
the proof will go through hyperedges.
This says that generically constructed expanders might not work, but possibly expanders coming from HDXs
Yeah,
might have this
yeah.
property. They overcome Bafna.
Sorry, I did not follow this. So this is what is the point here?
The point is just that like Bogdanov's precise example put two coloring on an expander, which had an issue at half. if you look at two coloring on an HDX, like this structured expander, the PCP which asks for neighborhood things will have error 0. Like there's no counter example anymore. Right, because triangles, like local neighborhoods witness that the global graph is not.
But here, even the whole graph will not be two.
Yeah, so that's exactly my next point. So, okay, this is fine. But the point is that we want to solve arbitrary, like we want a PCP for arbitrary 2 CSPs. Like it's fine that we solve this two coloring issue. But this may not solve like other issues. Maybe there are other issues with even on HDX. So you maybe like, 10 coloring on HDX, we need to show that the PCP error becomes smaller than half.
Oh, so given an arbitrary CSP, you're not reduced it to a two coloring on an HDX.
No. Oh, that is also one issue. Like firstly, we haven't reduced it. And second issue is like even given an arbitrary CSP or 2 CSP on HDX, we haven't shown that there is a PCP for it. We only shown it for two coloring, so 3 coloring. Whatever. So actually, it is true that what happens is that you can actually, even on HDX, you can construct other 2 XOR instances, not two coloring, but like other 2 CSPs for which the PCP value remains at half for the obvious neighborhood PCP that you consider. So that's the issue. So it tells you that it's not just about, having cliques or triangles in your graph. Like you need something more than expansion. And the one more issue is that in Dinur's PCP, like there are expanders are readily available to us, but random hypergraphs are not HDX. So like even constructing these HDX is hard. So we'll actually see this. Okay.
So you did solve this fact that locally it's a sparse graph, the one that you obtain by clickifying those hyper edges, right?
Yeah.
It's still a sparse graph and it does not look locally tree-like, right?
Yeah.
So that solved one problem.
That solves, it seems to solve the problem. So Bogdanov's barrier was like, okay, if you consider 2 coloring on generic expander, the PCP error doesn't reduce. So if you consider 2 coloring on an HDX, the PCP error is small, but you have to show it for every 2 CSP. Like you have to consider like the prover, right? Like there might be any 2 CSP on an HDX and you have to show a PCP for that.
Yeah, but what is the stronger local to global?
Oh, that is just like neighborhoods are not tree-like. Yeah, it's just.
No, are you saying that there is some other?
That maybe that there is some other property of HDX using which maybe we can solve this issue. That you can, any 2 CSP that you're given on an HDX, you can reduce.
I need an example to process it. What is an example for PCP values?
For what?
Some easy example where the PCP value remains more than half after adding these cliques.
Actually, I will give a definition of what is the property needed to have this, like to go beyond half. And when it will be you'll be able to see that when that doesn't happen, you can.
Do we know that we have a counterexample in this case, or we don't know how to prove?
No, there is a counter.
There is a counterexample, okay.
So like Bogdanov type other counterexamples, even on HDX. That's the message.
Okay.
I have another question. So the thing about working with 2 colorability on a on a graph, on an expander graph, and somehow saying that if we were to try to PCPify it, then we run into problem. Is the issue that the starting problem is not an NP-complete problem, and therefore this is not giving us a PCP in general?
Actually, 3 coloring I could have said, but that will have barrier at 1/3. I just mentioned like the first barrier at half itself.
I see. So there's this initial thing where somehow if we want to do this for all of NP, we would probably want some reduction where
first.
Maybe you get into some sort of a K coloring of a special expander.
Yeah.
Okay.
So in Dinur's case, like this reduction is not hard. Like to get a 2 CSP on an expander, you just place an expander.
Okay.
But we'll get, like for HDX, it's harder.
Okay.
But that is a different issue. Yeah. Okay, so I want to say like at a high level, like what is this property needed to go beyond half? Like it seems to not just be that you have many cliques in your graph. There's something more. And this is the property. So like take a graph G, which is, this same graph that we had like after cliquifying your HDX. So take any graph G, we will say that it's a co-boundary expander if the following holds. So fix the graph G, but now take any 2 XOR instance on G, which means that label edges of G with 0 or 1. Okay, and so is it clear like what's a 2 XOR instance on G?
So what does the edge mean? One mean? I mean, like.
Yeah, so this instance, for example, corresponds to a 2 CSP, which means that you want this variable plus this variable to add up to 1 over X, F2.
Opposite.
Yes, yeah.
So
Here
it's
you
a
want
special type of, it's a max cut on a subgraph of this problem.
yeah.
No. You're identifying vertices.
Yeah, so it's just generalizing 2 coloring. You
Yeah.
just have 2 lim.
Yeah, so alignments here are on vertices. Constraints are
Yeah,
on-
constraints are always on edges. Vertices you want to label with F2, like 0 or 1. And yeah.
It's two coloring with bits again, and
Yeah.
you're asking if the bits are the same or the constraint is
Yeah.
not just different colors but the same or
Yeah,
different.
yeah. So it's just 2 lin or unique-lin or whatever. But yeah, so now we want, now you can notice that, whenever the instance is satisfiable, like all triangles add up to 0. So this is a solution to the 2 XOR instance. And you can also notice that if it's satisfiable, 1 plus 0 plus 1 is 0, and so on. Like every triangle has to add up to 0 if your instance is satisfiable. Right, because I can add up the 3 equations on the triangle, and on the LHS I'll get 0. So RHS must be 0.
The edge value in every triangle of the triangle should sum to 0.
Yes.
Because if it is
Yeah,
satisfiable
just-
instant, every vertex value
Yeah.
is counted twice.
Yes.
But isn't that for the edges of the xi plus xj is either 0 or 1, and whether it's equality or inequality, maybe you're not understanding.
So I'm just saying that,
On each edge of a function, it should be the sum should be 1 or 0.
yeah. So look at the constraints, which will be like x1 plus x2 equals 1.
Yes.
The next constraint, if you have a triangle, it will be like next constraint will be x2 plus x3 equals 1.
So I think here the thing is, the assumption is that the constraints on the triangle, like if I look at every triangle and add up the edge values, they are all turning out to be 0.
Yes.
And the consequence of that is that the vertex thing should also be 0.
Okay, so it's the opposite. So I'm saying that here, this instance is satisfiable. So there exists a true assignment to the vertices, which satisfies all the edges.
Okay.
Oh, as a consequence, you must get that every triangle must have an
Must-
even number of ones on it.
Yeah.
I see.
Oh, just the vertex, adding just the vertex.
There's a vertex solution which implies that you must have.
And the edge thing should sum to 0.
Should I write it on?
Okay.
Maybe I'll just write it here. So I'm just saying that, like, you have, for example, this is the 2 XOR instance. So this 2 XOR instance is just saying A XOR B should be 1, A XOR C should be 1, and C XOR B should be 0.
Yeah.
So this is satisfiable, and that's just because, like,
So the
if you add it up.
The edges sum.
The edges sum to 0.
Yeah.
That's the
Yeah,
consequence of the fact.
What is
Because,
it?
Just because every vertex is being added.
Yeah. No, yeah. So
Yeah.
it's like if you know that your instance is satisfiable, then
Then-
you must have this property on
Yeah.
the edge layer. Okay.
Yeah, but what co-boundary expansion says is the converse also holds. So it says that I'll only give you information about the triangles. I don't know if there's a vertex solution or not. But if all triangles sum up to 0, there must be a vertex solution. So it's like a local, I'm only getting to see local.
But that's not special.
Yeah.
The
So,
graph is called a co-boundary expander if it
Yeah.
has this problem.
so if it's a C co-boundary expander, if you give me any 2 XOR instance, that is inconsistent on, let's say only epsilon fraction of triangles, like only epsilon fraction triangles do not sum to 0, then you can get a vertex labeling which violates only C epsilon fraction. This is like a very, very strong property. Most graphs won't satisfy this, or even random graphs won't satisfy. Or yeah, just think of the epsilon equals 0 case. Like if it's all triangles are consistent, I want there to be a vertex.
What about the expansion?
Yeah.
It's not defined at all in terms of what apparently an expansion property.
Yeah, so this is like a high dimensional notion of expansion in the sense like this firstly makes only sense if you have triangles in your graph. So that's why it's high dimensional. And actually the way to define it for just graphs turns out to be combinatorial expansion. Where like you want every set to have many edges going out.
Usual expansion is thing between vertices and edges. This is between edges and triangles.
Yeah.
Therefore, that's why
It's like the analog of checker.
Yeah,
Checker
exactly.
would want to say that if the cut size is too small, then one of your set sizes must be massive.
Exactly.
Then the set of the complement is massive.
Yes.
This is like going from edges to triangles.
Yeah.
it's the same cheater, but replace
The edges are all consistent, then there can't be too many triangles.
Yeah.
That are,
Yeah. So this Cheeger thing, in just you can define Cheeger, you can define spectral. In graphs, they are equivalent. Like there's Cheegers in whatever. There are so many things, but in higher dimensions,
This seems still talking about like this local versus global thing, right? I mean, why did it like okay? Anyway, I have to.
yeah. So it's one way to generalize Cheeger's definition to higher, and also complete graph will satisfy this. It's easy to show. Like with constant one actually.
So what you just said is for edges and triangles. Is there a variant which also works for like k simplices and k plus one simplices?
Yeah. But we only require it for edges and triangles.
I think we should go a bit easy on the questions because
No, it's fine. Like we can go through how much ever. Okay, actually, yeah, it's fine. I'll skip the last part. Yeah, because actually this definition is more interesting, I feel, because usual expansion is very spectral. Okay, so actually, of course, it's not true for all G. Just as an example, like if you take, just solving 2 lin, 2 XOR on given a graph is not an easy problem. Like we have all these other rounding techniques and so. Here we have a very simple algorithm to solve 2 XOR on this graph. We just count the fraction of unsatisfied triangles. That's a good estimate for the value. And actually HDX with this extra property of coboundary expansion will get you to error below half. And to your question, like if you don't have this property, there is some 2 XOR instance which violates the property. That's exactly the 2 XOR instance for which you won't reduce below half.
there is no description of that. It's just
Yeah, it is. So the PCP, like once you have this property for this HDX, the PCP will just be that you ask your prover to give an assignment to every clique in this graph. There are only theta of n cliques. So this PCP is actually linear sized for this 2 CSP. And we can show that the value drops to whatever constant you were aiming for, 0.01. And this overcomes this expander barrier at half. And the main ingredient is this so-called de-randomized agreement tests. Like given that the PCP reduction is immediate, and these were proved with Doer and Noam, and concurrently also proved by Dickstein, Dinur, and Lobotsky. Yeah.
But here the PCP length is just linear. There is no polylog at all.
Yeah, like given a 2 CSP on an HDX, you have a linear size PCP for it. So now the question is, how do you even get this, right? Like our arbitrary 3-sat problem is just a arbitrary graph. There's no such structure.
So should I take away saying that if we are able to convert Dinur's conclusion into a arbitrary
Yeah.
PCP on a co-boundary expansion,
Yeah.
then bringing the error down is not going to cause an additional
blow up.
loss. Yeah. Okay.
Yeah. Okay, so this is exactly the issue you pointed out. We don't actually have a full PCP because we have a PCP only if this is a very specific type of 2CSP, structured 2CSP. So what if your 2CSP you start out with is Dinur's 2CSP, which will be arbitrary. And that's the first part in our reduction. Like you start out with the arbitrary 2CSP. The first part is to reduce it to this structured CSP, which is an HDX. And this is done via this fault-tolerant routing algorithms on HDX. Okay, and once you have this HDX structure, like our alphabet blows up in this part, but let's not worry about that. Once you have this structure, you can use whatever I showed you now, these direct product tests to get down the value to 0.0. And the main thing is that this part, this arrow maintains the value. It doesn't drop the value too close to 1. To mention, because there's not too much time left, I'll just mention that earlier works used routing algorithms to change the structure of your 2CSP. The issue there was that they made the value become 1 minus 1 over log n, like in the no case. And then we can no longer use this. So the new part here was to notice that actually if you ask for stronger routing algorithms, like fault-tolerant routing algorithms, you can maintain the value. And finally, we use these tools for two-query composition, like Moshkovitz, Raz, and then Harsha, to reduce the alphabet from this huge thing to just a constant. Now, this is a black box application, previous techniques.
So the second blue arrow, does black box come from the existence of the direct product theorem? So you have to do a little more.
No, it's almost black box. It's like very simple lemma.
Okay.
Yeah, because in some sense, the direct product test is basically analyzing when you take two things and check whether they are consistent. Is there a global assignment? Okay. And here you're additionally checking constraints. Your verifier also checks them. Yeah.
So the main meat is the first blue arrow in the.
Yeah, the first and the previous works.
The previous works.
Yeah.
Okay.
Yeah, so we don't have time, so we can just.
No,
it's fine. I can maybe just define routing and not say like how it gets it. Maybe in like 2 minutes I'll define that. Okay, so actually this problem was very interesting that this problem already existed in the literature. It is called almost everywhere reliable transmission. It was defined by Dwork et al. Actually in the context of distributed computing and multi-party computation. So imagine a sparse graph where like all these players all these people want to communicate with each other, but they are not connected via direct communication edges. So they can only communicate via the edges in the graph. We want to design a routing protocol between all pairs where you can only transmit messages along these edges. So between these two vertices, you could use complicated protocols, like you could transmit to 3 people, take majority, and so on. So this is like one routing protocol. And the efficiency is, total computation time. So efficiency of the number of edges used in this protocol. So it's
for communication, not for computation.
Computation, as in like you cannot do crazy things. Okay, you're getting many messages, you're computing some NPR problem over. But if you take majorities and parities, whatever, it's fine. So roughly a proxy for it is just the number of messages sent. And we say these protocols, so you can construct like all pairs of protocols between all pairs. So first you have the graph, you construct all the protocols. And then we say this is fault tolerant if the following holds. So an adversary comes in and corrupts a bunch of nodes or edges in the graph. In the sense now, after that, in the protocols, these corrupted edges or vertices may deviate from the protocol arbitrarily, even adversarially. And you still want that if epsilon fraction of nodes are corrupted, like for example, these nodes are corrupted, many of the players, only like O of epsilon players may not be able to communicate with each other, but every two players, like 1 minus O of epsilon pairs can still communicate. Like, maybe these
the
are.
protocol is defined beforehand. So
Yes.
once the graph is there,
Yeah.
we need to come up with the protocol.
Yeah.
And the protocol is like for every pair, I need to say what they are supposed to do.
Yeah.
Few more. For which graphs support such a protocol?
Oh, I see.
Oh, okay, sorry. Yeah.
Which graph? The complete graph certainly supports a
Yeah.
protocol.
Yeah.
You want, are there sparse graphs for which support such a protocol?
I see. Okay.
Yeah.
Okay.
Yeah. So the main designing question, it's a design question, which is that you design a sparse network with, ideally constant degree network. And you have to design all pair protocols between all pairs such that these protocols are efficient and they are fault tolerant. So efficiency you want is like, if you have constant degree networks, you'll need at least log n length paths. So you want polylog n efficiency, you allow for some polylogs. And fault tolerance is like if constant fraction vertices are corrupted, you want all but some other constant fraction to be able to communicate.
Sorry, and the behavior of the malicious node can differ based on which pair I'm checking if they are able to communicate.
Yeah, can
Oh,
be
I see.
anything.
Okay. Oh, so it's more like if I decide that player A wants to send a message to player Z,
Yeah.
and now I say, okay, these nodes are corrupt. Is there a way in which they can mess up the communication?
Yeah, exactly.
Okay, and for every pair, the malicious nodes can now behave differently.
Yeah, they can. So malicious can do anything, but everyone else behaves correctly.
No, but his question was the malicious behavior. I mean, when you are trying to test a particular pair, then the malicious behavior is changing.
Yeah, that can be. So they can behave any way. In any
No,
way.
anyway, but any fixed way or like, I mean, you say
Depending on the protocol.
let's give a malicious behavior for every node. And now you want to check whether how many pairs are still able to communicate with each other. Is that what you're saying? Or are you saying that
They can behave in any. So like if A is transmitting to B and there's some node C in the middle, sometimes it could let the transmission go. Sometimes it could change the message being transmitted or anything depending on who's communicating. Yeah.
But everything is deterministic here?
Yeah. I mean, I don't
Including
know.
the protocol?
Yeah, everything is deterministic. Yeah. That's a good question. Yeah, so somehow the main part was to actually solve this question using HDX, like our sparse network is HDX, and you're able to get a polylog and efficiency protocols. That's exactly the polylog and blow up in our size, the efficiency, and the fault tolerance is constant, which is like maintaining the soundness turns out to be exactly the fault tolerance.
Is it, do we know that this can't be done on expander graphs? So you need HDX for the direct product theorem.
Yeah.
That's clear. But so it's clear that part needs the HDX, the direct product. But is it clear that this part also needs a HDX, or is it conceivable that there were previous works following Dwark et al. Who did this using expander graph but didn't get this theorem statement, a much weaker theorem statement?
Yeah. So it's for the previous work, they were not able to handle constant fraction of edge corruptions. They were able to handle vertex. So finally, they were not able to build like a constant degree network. Yeah, it's not clear that expanders cannot do it. I don't know what that would even mean, right? Like, that. Like, how would you formalize that? Like,
No,
expander?
manifest actually explicitly show that you can construct it using expanders.
Oh, yeah. Yeah, I don't know how to do it using.
Graph to be like looking at it
doesn't satisfy this problem.
Oh, yeah, one way to do that.
But sorry, I'm still getting, so this is just a question of, does a graph exist or not exist, right? I mean,
Yeah, this
so
is.
how is this showing up in a reduction? Like, how do you reduce something to this?
Oh,
or something like.
we are just saying that HDX supports this protocol. HDX.
Oh, I see.
Yeah, their question was design. Our question was that show that HDX support such a protocols. Like,
Oh, okay.
we just showed a
It's not
generic
like we
lemma.
are going to do something like, I have a reduction from 3 stack to graph construction, such that if it was.
Oh, no.
Okay. So the thing is, it's just that if we are able to show that HDXs can be made fault tolerant,
Yeah.
you can sort of use that in Dinur's.
Yeah.
You will completely now do a new.
It's a
You'll
new
embed an
reduction.
arbitrary CSP.
Oh,
I'll just-
inside a fault tolerant type thing. That's what you start off with.
Yeah.
Oh, I see.
I'll
Then you see
taking the
you will
construction.
put it on a fault tolerant.
Yeah, so the thing is like I skipped the whole construction. Just the main idea, like why this helps is you're given a 2 coloring on some arbitrary graph or 3 coloring or whatever. And you want to embed it like on make it convert it to reduce it to a 2 CSP on a structured graph. And we'll use that these support fault tolerant protocols. And kind of the idea is here, a verifier would query a random edge, but this edge, let's say, ij is not present here. Let's say ij here looks like that. I looks here, like imagine number of vertices is equal to number of vertices. So ij here is connected by an edge, but not by an edge here. So you basically ask the prover to provide a routing of i's labeled to j. So that's where like routing already showed up in previous PCPs. It's just that here, like this fault tolerant routing, if the value here is 0.99, the value here remains 0.9. And then, that's just fine.
When the number of queries is very small,
Yeah.
is there a reason to think that algebraic techniques will not give constructions?
Yeah, there's no such reason, I guess.
But
Here, like the good thing about HDX based things is like somehow you can abstract out the expansion properties required and just work with the
it's almost,
abstraction.
Dinur's PCP is almost is the starting point of.
Yeah, it's like the same techniques as like the same idea.
But we said by the way, Dinur's result also we don't have an algebraic proof of it. No?
Yeah.
So even a much simpler question, we don't have an algebraic.
So what is it that, where's the obstruction? It's not the size, because we know how to construct n, even order n size PCPs with using algebraic technique.
No.
No, isn't this sort of AG code based construction? That's just one thing.
That's they hide, they cheat in the statement of the theorem. It cannot be used for PCB construction.
What about Benson Sudan?
Benson
Oh, yeah.
Sudan.
Yeah, that is required for
That
this.
is it. To get Dinur's result, you need Benson Sudan. Just Dinur will not give you that statement.
Yeah, we don't know combinatorial proof of Benson-Sudan or like algebraic proof of.
So the statement that the n polylog n constant requires both Benson-Sudan and gap amplification. It needs both, and we don't know how to do it just using. So just Dinur's gap amplification proof will not get you n polylog n. It will get you poly n. To get n polylog n, you have to first do Benson-Sudan and then do gap amplification over it.
Yeah, actually, one thing to mention is actually we could also do Benson-Sudan, and our this first arrow actually also gives a gap amplification. So it's a new way to get the Dinur's result. Yeah. Any more questions?
So there are too many steps in this. You know the areas, Benson-Sudan, all of them are going on.
Actually, We can skip this. Actually, this arrow gets. I could have stated already. Like you can go back and this arrow.
Yeah, you can put any branches on.
Yes.
The gap is down.
Yeah, they call it.
This is.